So far, we've looked at what lags and leads are and how they're commonly used to help you begin to identify these as areas of risk within your program. We've also looked closer at lags to cover why it's best practice to avoid them and how we can get around the issues that lags bring by replacing them with dedicated delay tasks. This third video will now cover why it's best practice to avoid leads by discussing how they take flexibility out of your program and encourage you to leave out detail that can save you. As well as this, we've also got an example of a risk list lead used to show you. Just like before with lags, following these guidelines will take you from just identifying common lead uses as areas of risk to being able to avoid the risk to begin with, or to fix it if you see leads again in other programs. Okay, so we know already that a lead is a tool commonly used to model a negative delay, or in other words, a delay that reaches backwards in time to another event. I've got Project open here with the basic lead example that I'll use to help illustrate what I'm talking about. Looking back to scenario 2, we had 3 bays of foundations and block work. We needed the block work to start 5 days after the foundations start to give enough time for the first bay foundations to be put in before the first bay block work goes in after it. We've used a lead to make these tasks overlap in a way that appears to reflect what we want to happen once the project starts. The major issue with a lead like this is that its duration doesn't automatically update if the duration of the trigger task changes. Say for whatever reason, there's a problem with the Bay 2 foundation installation, and this means that the overall foundation task takes 20 days rather than 15. Updating the duration of the foundation task doesn't update the lead with it. The lead still counts back only 10 days. You have to remember to manually correct the lead length, otherwise the block work would show as starting 10 days after the foundation task begins, rather than the 5 that we originally intended. This can have big knock-on effects to your critical path, and this is just for one lead. You could have multiple leads in a program, all with the potential to go wrong like this. It also needs to be said that we're creating a problem by representing all 3 of the bays with only 2 tasks. Setting up the program like we have it here makes it very difficult to detail how an issue with Bay 2 might cause an effect later on down the line. It assumes that anything that follows on from the works in the bays depends on all of them finishing, not just single bays as would be the case in reality. Using leads like this encourages us to set up the program tasks in a way that can make it difficult to follow real program logic and to illustrate any problems or deviations from the plan once work starts. Finally, just like with lags, leads are prone to the same problems in that they don't have a great way to describe what they represent. Again, you could use the notes method I talked about in the how and why to avoid lags video by double-clicking on a task to open the task information and typing in your explanation for the lead here. But once again, you've got the same problems in that they need their own thought, you and others have to know how to access them, and they don't appear automatically on the Gantt or a printout. At a glance, while it may look okay to use leads like this, they actually cause you to sacrifice the flexibility of your program when you really don't need to. Leads like these, and many other similar use cases, do not work in your favour. Okay, so what should you use instead of a lead? I'll show you by fixing scenario 2. Using leads to make tasks overlap like this is actually a symptom that the tasks need to be broken down into smaller sections with relationships that represent the project activities more accurately. We know that there are 3 bays of foundations and block work, but we've separated all of this into only 2 tasks. If we break down the foundations and block work into separate tasks for the 3 bays, it means that we're designing the program in a way that reflects the fact that things inevitably do change. When things do change, we can also get into illustrating this quickly and easily. Okay, so I've split the works into 2 summary tasks, one for foundations and one for block work. Under each of these headings I've got the segment of the works for each bay. In other words, we've turned 2 tasks into 6. Putting the logic in for this, we know that each foundation task can just follow on from each other. So the Bay 2 foundations have the Bay 1 foundations as a predecessor. And the Bay 3 foundations have the Bay 2 foundations as a predecessor as well. Now for the block work, we know that the first block work task was looking to start after the Bay 1 foundations had gone in. Now we can model this properly. We give the Bay 1 block work the Bay 1 foundations as a predecessor. In fact, each Bay block work task follows on only from their corresponding foundations. so we give the Bay 2 block work the Bay 2 foundations as a predecessor. And the Bay 3 block work gets the Bay 3 foundations as a predecessor as well. Now if something goes wrong on Bay 2, say the foundations take 10 days, it doesn't push out the line of work for Bay 1. Anything connected to the completion of the Bay 1 block work will be unaffected. In reality, your teams will swap over to work on Bay 3 while they wait for instruction on Bay 2. Writing the program in this way allows you to track and reflect these deviations from the plan as they happen. Another thing to mention is that if you begin to populate the plan with resources, this way you gain greater awareness of where overallocations will arise. So putting in Masonry Team A for each of the blockwork tasks shows that because of the duration of the foundation tasks, the blockwork task resources overlap. This gives you insight into how to achieve the original target of 18 days for the blockwork. You could bring in an additional team, Masonry Team B, and have both teams work on Bays 2 and 3, which for a fixed work amount on the blockwork task reduces the total time for blockwork to 13 days rather than 18. Alternatively, you can leave just Masonry Team A and accept that things are going to take longer than originally planned. Either way, it sheds light on what your options are. This method avoids interfering with the critical path by including a detailed, logical chain of events, rather than leaving it as two single, vague tasks that we've programmed to play out more on the basis of assumption than actual logic. Unlike lags, we do have an example of a riskless lead use scenario. You can safely use leads to set up a flag warning for the latest date to make a procurement order, just like I've got here for a precast concrete example. Setting up the logic in this way has no bearing on the critical path whatsoever. You can attach the installation of the precast wherever you need to in the program, and the procurement deadline will move with any changes in the forecasted start of the precast installation. Okay, so to summarise, you can essentially see that leads encourage you to leave detail out of your program, and it's this that comes back to bite you more than anything. This is why we say it's good practice to avoid leads and include the deeper level of detail which allows you not to use them. Doing this also avoids the assumptions masked as logic from interfering with your critical path and can also give you greater insight into your resourcing options and overall work strategy. Again, following this method rather than using leads will save you from wasting precious time and resources trying to solve issues that are difficult to foresee. Okay, that's it for this video. This is quite a broad topic, so if you are confused about any of it, please be sure to contact us via JustAsk at menlo-academy.com and we'll see what we can do to help you out.